Was there a moment in your research when you knew that you had discovered something so monumental?
It started off as a single electron being able to tunnel through a barrier. And what the MQT thing really said that really convinced us that we had something was that much bigger things could tunnel.
Thank you so much for joining me today. So first of all, I would love to say congratulations for the Nobel Prize. And we're here to talk about your research. So last year, we celebrated 100 years of quantum physics. And of course, it started with the microscopic scale. But in the 1980s, could you take me back to what was the motivation to start your research and what you were trying to achieve with the chips that you were designing?
I was a beginning graduate student at the time. I took a class from John as my senior as an undergraduate, and I was really fascinated that they were looking at these superconducting devices and seeing quantum noise effects in it. And, as a student, you're really fascinated about quantum. Electronics was kind of my hobby, so it was very natural to want to come work with John and do that. And then while I was a student and Michel came, we were learning about this idea of macroscopic quantum tunneling from Tony Leggett. And we just decided this would be a worthwhile experiment to do and to do it well, really trying to pin down the effect and understand it, measure it very precisely.
I remember, I joined John Clarke's lab as a postdoc, and at the beginning, it was not exactly clear what I would be working on. There were several possibilities, but John had attended a conference by Tony Leggett at a moment where he was proposing to the community to do experiments checking whether macroscopic variables obey quantum mechanics. And we launched this project. It was fantastic for me because I wanted to work on the foundations of quantum mechanics for a long time. But during my PhD, which was in NMR, I had only used quantum mechanics. There was no possibility of checking it.
Interesting. So can you tell me, because you have these superconducting wires with the insulating layer in between, and then you have the Cooper pairs that are traveling through them. Could you explain maybe what a Cooper pair is for our audience if they haven't heard of one?
Yes, well, a Cooper pair is if you want, the smallest unit of the superconducting order. You can describe a superconductivity as the pairing of electrons. But in our experiment, these Cooper pairs actually play a sort of only a role in the background. The aim of the experiment is to check whether currents and voltages obey quantum mechanics. We had to use a superconducting circuit because we wanted to have a minimal amount of dissipation, but also a very strong nonlinear electronic response. And
What?
if you want superconductivity and Cooper pairs and Josephson junctions at that time were the most, if you want, the type of system that was most likely to be successful in this search for macroscopic quantum phenomena.
And the material that you used for the insulating layer, could you tell me about how you chose the material there?
It's often just the natural oxidation of the material. For example, going back a long way, people were making tin to oxide tin junctions. And it turns out that the tin is a very easy way to grow a natural oxide layer. And then you deposit the second superconductor on top of that.
Excellent. And yesterday in your talks, you were talking about some of the systematic challenges when you were doing your measurements. So could you talk me through some of the challenges? And especially for early career folks, it's nice to hear that things don't always go so smoothly when you're doing your measurements.
Yeah. How far back do you want me to go?
As far as you would like.
I was a graduate student who began my work in University of Cambridge, the Royal Society Bonn Laboratory, in 1964. And one of the more senior students there, who'd been there for 2 years, was named Brian Josephson. And it was Brian Josephson who actually invented what became the Josephson junction. And I learned an enormous amount from him. And he won the Nobel Prize some years later for this work. But he was an absolutely brilliant guy.
Excellent. And so what did you learn from working with him that you were then able to carry through to your research later?
Well, I think for most of my career, what the kind of research I've done has been based on Josephson junctions in one form or another. And for example, one of the things that was invented a few months before I became a graduate student was something called the SQUID, which is a superconducting quantum interference device. You have a loop with two Josephson junctions in it, and it's an incredibly sensitive detector of magnetic field.
John had combined electrical engineering ideas with superconductivity ideas. It was this union of two fields. On one hand, condensed matter physics and superconductivity, but on the other hand, electrical engineering and instrumentation, electrical instrumentation. This is what this is the essence of the Josephson effect. The Josephson effect was incredibly new in that sense that it unified two fields of physics that were thought as quite distinct. The world of electrical engineering with macroscopic currents and voltages on one hand, and the world of superfluidity and superconductivity, which were hardcore condensed matter physics phenomena.
Is by the time I arrived in 1980, early 80s, the Josephson effect was well established. It wasn't surprising anymore to a new student. You learned about it. And also in John's lab, we invented a lot of ways to make these things. So the actual Josephson junction we made in the thing was actually much simpler than, let's say, what I had done with the SQUID experiments before that. So that was, in some sense, the easiest part of the experiment, is building that.
Yeah.
The hard part, kind of as Michel alluded to, was the electrical engineering and what the junction could be connected to. And I think the most important thing we realized very early on is that this experiment was really sensitive to noise. After all, you're looking at quantum effects. So that we had to design these things called filters so that any noise from the room temperature or even at 4 Kelvin wouldn't come in and swamp the device. So, initially we didn't do that so well, but we tested it anyway. And we had problems. It was very clear. And then we worked very hard to understand how to filter. And I think Michel's background from NMR and powdered NMR samples really brought us into the idea of building these filters right.
And was there a moment in your research when you knew that you had discovered something so monumental?
Yes. By the end of the experiment, I think we were very much aware that we had built artificial quantum systems, and the idea of artificial atoms was something that came rather obvious at the end. What was missing was the quality factor, the low dissipation. That it took several decades for our system to really improve and reach the level where they are today, where they can compete with atomic physics.
Yeah, and I think that the discovery in the end was sort of two pieces. And the first one was the fact that we were able to observe quantized energy levels in a macroscopic system, which had been forever the purview of atoms and molecules. And it was that discovery that I think really began to convince us that we had something that was really interesting and new. And in fact, our award was really based on two quite short papers, two physical review letters. And the first of these was the observation of quantized energy levels.
And you mentioned other people working on this. And one of the things I loved in your talks yesterday was the emphasis on collaborators.
Oh, yes.
Oh yes,
Yes. Oh, yes.
yes. But when you receive a Nobel Prize 40 years after your initial work, it means that many people have contributed to the field.
Yes.
And I think what was very special about the field is people chose to do different things. It's not like we were trying to beat each other by a couple months, to publish a paper. And because of that, we explored the physics in a really good way, in different ways. Everyone had their own kind of personality to it. And that really helped the field develop over time. And we were really dependent on other people making discoveries in order to understand how to build these systems better.
I always like to do a little story about the 40 years because our first publication was on October the 7th, 1985. And I got a phone call in the morning at about 2:00 from the Nobel Foundation to say that the three of us had won the Nobel Prize. And that was on October the 7th, 2025, 40 years later to the day after we published the first paper. And I think it's not that anyone had looked that up, but just that it happened to be the particular day of the week that the Nobel Foundation made this announcement.
And how did you feel when you got the phone call?
I was skeptical, but it was. I kid you not. I mean, I was a little bit nervous about this. Wasn't real.
Yes.
There's a history of people prank calling this, so
Yes.
you have to be kind of careful.
I asked the person who called me 2 or 3 questions about me in particular that he answered correctly.
Very good. So you verified the.
Yes, I asked him, for example, where I did my research, for which they were doing. And I
didn't know that, John. That's great.
Oh, I did.
I
Yes.
think
And
this is
I asked them if they knew the school that I had been to. But fortunately, I had looked all this up. So after they got this correctly, I said, well, then I believe you. Just going back for a moment to these 2 physical review letters. The first one I mentioned, and the second one was published just 3 weeks later. And the subject was really on what's called macroscopic quantum tunneling, because tunneling was something that people had worked on and understood for many, many years. It started off as a single electron being able to tunnel through a barrier. And what the MQT thing really said was that much bigger things could tunnel. I mean, you could imagine something the size of my thumb being, able to tunnel these days. And I think it was the combination of these 2 things that really convinced us that we had something.
Brian Josephson invented the Josephson effect, but in that effect, the macroscopic variable is what he called the gauge invariant phase difference between 2 superconductors. But even him did not imagine that this variable could be quantum. In his papers, it is always treated as a classical variable. So if you want, the upgrade that was made by Tony Leggett was to say that this macroscopic variable could be itself be quantum. So that was a different layer than the underlying electrons and Cooper pairs of the Josephson effect. That was quantizing a variable at a level which was well above the usual quantization that you see at the level of electrons or Cooper pairs.
Yeah, there's no doubt that it was Tony who got us going, and I had known Tony for many, many years. And I don't know if you know this, but very tragically, he died just 8 days ago. But he was the guy. He was the person who got us going.
I'd like to paraphrase what Tony Leggett said. He said, when you have an idea and it's original and your colleagues do not agree with it, keep persisting and work on it until you are successful. So he was in this position of proposing something that was contrary to the common belief. And many people dismissed his ideas. Even I remember Nobel Prize winners laughing in his back. And he kept at it, and it was, in the end, it was very fruitful.
But for example, with Tony Leggett, he had this idea, but he really fleshed out the physics. He talked about it. He did,
Yes.
well, for example, the effect of dissipation on tunneling, which is very new and important. So we worked through that so that there was, it was a solid body of work that we could look at and decide to work on. And that's part of having a new idea that maybe is a little bit unusual.
So you have to be persistent, but you have to be also very solid.
Yeah, that's right.
That's
Exactly.
the example that Tony
And that's what you always have to do if you have a new idea. You really have to think through to make sure that, all the kind of objections are met, that are understood.
Well, thank you so much for joining me today. It was fascinating talking with you all, and congratulations again.
Thank you. Thank you.
Thank you.